All right, everybody. In this video, we're going to go over the 6.6 notes, which is on geometric sequences. So we're going to do a couple things. We want to identify what a geometric sequence is. We want to extend some geometric sequences and graph them, and we're going to see what they look like. And the last one is to write geometric sequences as functions. So how do we write them? So it's kind of the idea for today. So first thing we want to kind of do is just kind of, if you were to enter all these numbers onto your calculator, if you were to do this keystrokes on your calculator, so type of 3, then you hit enter. And then if you do times 2, okay, so what's going to pop up on your calculator is the first thing, if you type in 3 and then enter, you can get a 3. And then times 2, you get 6. Times another 2, and you hit enter again. You get 12, and 24, and 48. And so the key thing here to notice is, like, if you look between these numbers, what's going on here? Between 3 and 6, we're multiplying by 2. 6 to 12, we're multiplying by 2. 12 to 24, you multiply by 2. And then same thing again, 24 to 48, we're also multiplying by 2. Okay. Same thing on the right-hand side here. If we type in 64 and then hit enter, and if you go times 0.5, so the first number that would pop over to be 64. If you hit times 0.5, you get 32, and then 16, and then 8, and 4. And again, if you just look here, what's the pattern that's going on here between all these numbers? Here we're cutting in half, and remember, dividing by 2 is the same thing as multiplying by a half. Right? Dividing is the same thing as multiplying by the reciprocal. So we're just multiplying by 1/2 each time as we go down. And that's going to be the idea behind geometric sequences, is that we're just multiplying by some constant ratio or some number each time. So if you think back way back when, and we did arithmetic sequences, we were adding or subtracting the same number each time. Okay, now we're going to be multiplying, and that's kind of the idea here. So what is an actual geometric sequence? Geometric sequence is, type out this definition here, the ratio between each pair of consecutive terms is the same. This is called the common ratio. Each term is found by multiplying the previous term by the common ratio. So then that common ratio, so up above we had our common ratios were 2 and 1/2. Okay, so it's the number that you multiply between each consecutive terms. The common ratio is the number that you multiply by to go between terms. And then again, here, keyword being common, so that number is going to be the same. Okay, so now let's take a look at a couple examples as we kind of go through this. So this first sequence here, so we're going to determine if it's geometric, arithmetic, or neither. So remember, geometric, we're multiplying. Okay, arithmetic, we're adding. And neither is just neither. So the first one here, how do we go from 5 to 1? We are subtracting 4 each time. We're adding -4. Same thing here, adding -4, adding -4. Okay, and so because we're adding or subtracting by the same thing each time, this is an arithmetic sequence. And I want you to think back, well, what do these look like? We kind of graphed these a while ago, right? If we have this constant rate of change, okay, this is like a linear function. Now on the next one, okay, how do we go from 1024 to 128? Same thing between 128 and 16, or 16 and 2. Sometimes it's easier to look at the smaller numbers first. So to go from 16 to 2, we just multiply by 1/8. So then once you kind of get an idea, so times 1/8. Once you get an idea of how to what you're looking for, then you can check the other ones. If you do 1024 times 1/8, it's 128. And then same thing in the middle one. If you do 128 times 1/8, you also get to 16. So here this is geometric because you're multiplying by 1/8 with a common ratio of 1/8. And then here on the side, just as a reminder, geometric equals multiplication. Arithmetic addition. So now moving on down to the bottom. So if you want to write the next three terms in these sequences, okay, we just got to first of all find the pattern and then kind of just keep extending it on. So it's kind of the second learning target is to kind of extend these sequences. So now we got to start looking at, well, what are we doing? What are we doing in these sequences? What's the pattern here? So how do we go from -2 to +4? We are multiplying by -2. Okay, -2 times -2 is a +4. How do you go from 4 to 8? Or 4 to -8, sorry. You're multiplying by -2. Okay, 4 times -2 equals -8. Same thing on the last one, times -2. Okay, so now if we keep following this pattern, 16 times -2 is -32. Okay, and if we keep following the pattern, if I multiply by -2 again, I get +64. And then if I multiply by -2 again, I get -128. -128. So your next three terms are -32, 64, and 128. Okay. Looking at the next one, what's going on here? So between 1 and 3, we multiply by 3. 3 and 9, we multiply by 3. 9 and 27, we multiply by 3. So our constant ratio here is 3. Okay. And so now if we just keep following the pattern, 27 times 3 is 81. 81 times 3 is 243. And then times 3 again, you get 729. 243 times 3. Okay, so these are your next three numbers in the sequence. Moving on here, graphing the geometric sequence, and we've kind of looked at these already when we graphed exponential functions. Because remember, when you did an exponential function, you're multiplying by the same thing each time. So if I just draw some axes in here, right, and then each one of these represents a term. Okay, so your first term here is 32. Okay, so if x is like, if I think it's like an xy table, right? We have 1, 2, 3, 4, right? Each one of these represents a term. Okay. And we can kind of just graph these points in the graph. 32 is not going to fit, so I'm going to start at 8, and then 4, and then 2. So let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. And then the fourth term in the sequence is 4. So then 1, 2, 3, 4, 1, 2, 3, 4. And the fifth term is 2. So 5, 2. Okay. And if you kind of keep, I'm going to keep doing this pattern a little bit. So the sixth term, the next term after this, if we keep multiplying by 1/2 here, so the next one's going to be a 1. And then the one after this is going to be a 1/2. If I keep multiplying by 1/2, so 1 times 1/2 is 1/2. So it gives us a little bit better of a picture. Now I can connect these, and you can see that these are just like the exponential functions that we graphed before. So now moving on to the actual writing of these functions. How do we write these functions? And so here we're telling you what the first term is, and then we're telling you what the ratio is. So R is going to represent a ratio. Write that in. R equals common ratio. All right. So if we know our first term is 1, so we can write that down. Okay. So A1. So here when you see this A sub n, this n represents your term in the sequence. So let me highlight that. This n represents the term in your sequence. So like up above, right, we had 32 was our first term, right? 16 was the second term. So it's A1 is 32, A2 is 16, A3 is 8, and then so on and so forth. So if I want to write the first term, we have A1 because we told you A1 is equal to 1. Okay. And now if we keep, and now we tell you, the next thing we tell you is that the ratio is 5. So here we're going to multiply by 5. And so then I know the second term in my sequence, A2, is going to equal your first term in the sequence, A1, times 5. Okay. But we know what A1 is. A1 is just 1, so 1 times 5 equals 5. So we know the second term of the sequence is going to be 5. Now if I do the third term in the sequence, so A3, okay, I'm going to take my previous term, and again, I'm going to multiply this by 5. So A3 is going to equal A2 times 5. And then we'll kind of fill that in, and we get 25. Right, so each time you're going to take the previous term and then multiply it by 5. And so then that kind of leads us to this definition that we have below, which is how do we write the equation of a geometric sequence? So let an be the nth term of a geometric sequence. So again, n is just the term that you're looking at. And the nice thing about this is that once we write this equation, if we tell you to do the 40th term, instead of expanding out the sequence, until you get to the 40th term, you can just put in 40 for n. Okay. So if you want to find the nth term of geometric sequence, where you have a first term A1 and a constant ratio R, and the equation you're going to use is A1 times the ratio to the n minus 1 power. Okay. So again, I'm going to highlight some things. So A1 is the first term, R is your constant ratio. And then we're just going to put it into this equation right here. So for example, in this first problem, we have A1 equals 13. That's the first term of the sequence. Okay. Now the next thing we got to find is what's our ratio. Well, from 13 to 26, I times 2. 26 to 52, I times 2. And then times 2 again. Right? I'm timesing by 2 each time. So R equals 2. Once you have all this information, we're just going to plug it in. We have A sub n equals A1, which is 13, times 2 to the n minus 1 power. Okay, so this right here is your equation. And so now all we need to do is, now you have to read the second part of this question, just find A7. All I'm doing is see how 7 is in the position of n, right? So I'm just going to substitute 7 in for n. So we have A sub 7. Okay, so again, compare these two, right? N is equal to 7. Equals 13 times 2 to the 7 minus 1 power. Okay. Now, big thing here, remember PEMDAS. And we're going to do exponents first, and we're going to deal with everything in there. So this is the same thing as 13 times 2 to the 6th power, 7 minus 1. Okay. Do your exponent, and you kind of simplify this down, and you get 832. Moving on to the next one, we can do the same thing. Here we have A1 equals 432. The ratio is 1/6. You can kind of look at these and go 1/6. Okay, and so when you write this out, you have A sub n equals 432, that's A1, times 1/6 to the n minus 1 power. Okay. And the second question here, find A15. We can plug that in, and we get A15 equals 432 times 1/6 to the 15 minus 1 power. Okay, if you type all that into the calculator, you get 1/181398528. 8528. And this becomes your final answer. So what's nice about this equation, again, is that we can plug in any number that we want to for n, right? N representing the term that you're looking for, and you can get the answer. So we can put, if we wanted to find the 15th term, all we have to do is plug in 15 for n. That's pretty nice. Okay, moving on to the last question. A badminton tournament begins with 128 teams. After the first round, there's 64 teams. After the second round, 32, so on and so forth. Okay, how many teams remain after the third and fourth rounds? Okay, now here in this problem, what is our A1? Think about that. Okay, think about what is A1 and think about what the constant ratio is going to be. All right, so our A1 in this problem is 128. Our ratio, we're cutting in half each time, is just 1/2. Okay, so then we can write our equation, AN equals 128 times 1/2 to the n minus 1 power. Okay, and quick reminder, if you want to double check your equation, Okay, real quick, you could just plug in, for example, 1 in for n. The first term, you have 1 minus 1, which is 0. Anything to the 0 power is just 1. So this whole exponent just becomes a 1, this whole term here. So you're left with 128, which is what we want because we started with 128 teams. Okay. And so then you could plug in 3 and 4, and you can kind of figure out that the third round you'll have 16 teams. Fourth round you'd have 8 teams. Fifth round you'd have 4 teams. Okay. So again, key ideas from this video. Geometric sequences, we multiply by a constant ratio each time. When you write your geometric sequence, you use your first term and your ratio. And then when you want to plug something in, once you want to find a specific term, you just plug in that value for n. Okay. And the last thing, we kind of graphed them a little bit, where in the graph, we saw that was basically an exponential function. And so we can kind of plot those values, where we use your x value is the term number. Right, so in the example that we had our first term was 31, so we had 1 comma 32 as an ordered pair. And we kind of went through that. Okay. So that's it for this video. If you guys have any questions, as always, let us know. But if not, have a great rest of your day.